Hey there, everybody. Welcome back to section 7.8. This is part 2 of section 7.8, looking at slope fields and phase portraits and trajectories and whatever of systems with repeated eigenvalues. So the point of this video is just to do that, right? Look at those pictures. Okay, so here is the system from the previous video. This is the example we fully worked out. It has a picture that looks like this. So at the very least, it's worth noting there is no spirally behavior here, right? This does not look like the eye of a hurricane or something at the origin. And the reason is because, as we saw with this example, there was no trig in the answer, right? The repeated eigenvalue in this case did not produce any trigonometry. And that will be the case for any 2x2 system with repeated eigenvalues. You won't get any trig, and the trig is what causes spiraling. This picture here, if you think back to section 7.5, looks a lot like a node, if you remember that picture. So there's an eigenvector here cutting through the picture, sort of dividing the plane into two halves here. And notice along there, the lines are sort of parallel to this vector. They're along that vector, but then this vector in this case acts like a repeller. If you just reverse these arrows, right, and have them go the other way, it would act like an attractor. So anyway, this repeller, what happens is trajectories that are close to the eigenvector are sort of parallel close, and then the eigenvector line throws them off, and they sort of turn around and then end up being parallel later. So here's sort of a trajectory path. I start down here, I get thrown away, and I sort of like eventually loop around like this and go the other way. So that's what these pictures look like with repeated eigenvalues. Since there's only one eigenvector here, you don't get this sort of chopping of the plane into four pieces, from using the two eigenvectors to chop. There's only one eigenvector line here. Anyway, here's what a phase portrait looks like. So here are some trajectories. Again, close to this eigenvector line, this bolder blue one, things are parallel to it, and then they get sort of like tossed away, and they kind of like loop around, and in the long run, they'll end up being parallel to this eigenvector line. Parallel-ish, anyway. This kind of behavior is called an improper node, to distinguish it from the nodes we saw in section 7.5. And this is kind of a heuristic or something here, so don't take this as gospel. But if you want to distinguish these pictures from the node-ish pictures we saw back in 7.5, this is kind of what you're seeing. That close to the eigenvector, things are parallel, then they kind of like tail off and then kind of loop their way around and end up going parallel in the long run the other way. And as always, you can separate out from the trajectories an x1 plot or an x2 plot, whichever one you want. So let's think about something over here, maybe. I don't know, right? Just whatever. Let's think about over here. Okay, so suppose you start like in this mess here. x1 initially is going down because you're moving to the left, but then somewhere around here, right, you sort of turn around, and eventually it'll end up going off to infinity in the positive direction. X1 will, because you're going to the right. That's what this plot here kind of looks like. X1 is decreasing for a while, but then it turns around and ends up shooting off to positive infinity. So again, sorry if that wasn't clear. Start down here, right? Somewhere in this jumbled mess, start. So let's follow this trajectory. X1 decreases for a minute, right? Because you're moving to the left. But then this guy turns around and will end up moving to the right like this if you follow it off the screen. So it loops around and eventually just keeps moving to the right. And that's how you get an actual x1 plot like that. Okay, so at the end of this, we are now at the end of chapter 7. We now know how to solve lots of different kinds of linear systems of DEs. If the linear system has distinct eigenvalues, either real or complex, we know precisely what to do. And in the 2x2 case, we know what their pictures look like. If there are eigenvalues that are repeated, we only really know what to do in the 2x2 case, but we can do it, and we know what the pictures look like there also. Okay, so at the end of chapter 8, now we're going to move into the epidemic model unit next. All of this stuff will come back in full force in chapter 9. So this chapter had basically two big purposes. Well, three. Okay, so the first purpose was just to get you comfortable with systems of DEs. The second purpose was just to get you familiar with their notation, like writing these things down. And then the third purpose is that in chapter 9, the nonlinear systems there, the ecological models, will need all of this. So all the language we developed here and all the pictures we drew, they will come back in full force in Chapter 9 to model things like predator-prey interactions or competing species interactions. This stuff here will be less relevant for the epidemic model stuff, for reasons that will become clear as we move through it. However, this section or this chapter is still valuable for the epidemic model stuff because it gets you comfortable with the notation and the concept and whatever else of systems of DEs. So anyway, that's where we're going now that we've wrapped up Chapter 7.